Namaskaram everyone. So I am Chaitanya. So my group works in the area of computational chemistry and material science. In today's talk, I will try to discuss a few aspects that are related to the hot carrier generation in the metal nanoclusters, specifically silver and gold nanoclusters, and the basics surrounding that. Okay, so the talk will not be more into the nanocluster and hot carrier, but more into the basics and how do we understand this quantum mechanically, how do you calculate these properties, etc. So please be prepared that there will be equations, but it is my duty to explain you the equations. If you pay attention, I will try to do that part. Okay, so in general, as a computational chemist or a material scientist, we see any material as simply as a bunch of atoms. They are like m number of nuclei and number of electrons are there that are interacting with electrostatic forces, Coulomb forces. So we generally deal with two kinds of scenarios. First scenario is for the case where the nuclei are fixed, where you are trying to optimize the coordinates of the electron. When we say optimize the coordinates of electrons, essentially we are optimizing the wave function. The moment you get the wave function, you will know all the properties. So for this fixed set of nuclei, what we are solving is nothing but the time independent Schrodinger equation. As you might know, this is also an eigenvalue problem, and these methods are what are called as the electronic structure methods. So the other scenario is for the moving nuclei. So specifically we need to solve the time dependent Schrodinger equation because nuclei are moving. So here at each and every nuclear time step, you will be solving the electronic structure problem. So in the time dependent Schrodinger equation, at every nuclear time step, you will be solving the time independent Schrodinger equation, get the energy, use that energy in order to drive the atoms. So there will be also higher level models where you will be completely solving even the nuclei as quantum particles, but that's not what I am referring to. I am referring to what is known as the mixed quantum classical dynamics. Okay, so these are essentially the nuclear dynamics method. So in the last talk you have seen probably the classical molecular dynamics, how it goes, as well as the coarse grained molecular dynamics. One step above that is these ab initio molecular dynamics methods, but all of these methods can be derived coming from the time dependent Schrodinger equation. So essentially those two scenarios are the ones that we will generally use in order to simulate any material or any molecule. So the dynamics can be divided into two specific varieties. The first variety is called as the adiabatic dynamics, where the wave function or the forces that are acting on the nuclei are coming only by one single potential energy surface. In general, the ground state potential energy surface. All of you have seen so many potential energy surfaces in the last talk. So if you consider catalysis or anywhere, you will see reactants, transition state, product, everything. So these are nothing but the ground state potential energy surface. If the forces are coming only because of one potential energy surface, it is called as adiabatic dynamics. On the other hand, if you have more than one state that is governing the dynamics, that is called as the non-adiabatic dynamics. There are many packages that are available. For example, in order to simulate the adiabatic dynamics, there are already now some packages, but relatively they are few in order to simulate the non-adiabatic dynamics. So when non-adiabatic dynamics is required is whenever there is a light matter interaction, or when the nuclear and electron motion are like strongly coupled with each other. In these cases, generally you need to consider the non-adiabatic dynamics. While we will not again go into the details of any of these things, we will start from the basics and we will quickly go through them. So using these things, these tools, whatever I have explained, my group works in some of these areas. One is like understanding the charge transfer dynamics in organic photovoltaic systems. Specifically here you will have donor acceptor systems. You shine the light. Then there will be a transfer of the charge from the donor moiety to the acceptor moiety. So these are the systems where you need the non-adiabatic molecular dynamics. These are energy storage materials. We design some next generation anode materials, as well as we try to understand the mechanisms of the solid electrolyte interface. All of you might be aware in a energy storage material there will be anode, cathode, electrolyte, etc. So when this electrolyte comes and interacts with the anode or the cathode, this electrolyte will decompose because there is some redox reactions, oxidation and reduction reactions will happen. Because of this, the solvent will be reducing or oxidizing and decomposing into products. So this formation, it is very important for us to understand, because in order for the ions to move, they should be going in a reversible manner, right? Like deposition as well as removal of that should be happening. charging and discharging essentially. For that, this solid electrolyte interface should be permeable only to the ions, and it should be insulating for the electrons. So these kind of things we study in our group. In addition to that, we also look into the various materials as well as methods in order to simulate the water pollutant degradation. And finally, we also are started to use this quantum computers in order to simulate molecules. Okay, so in today's talk, our major aim will be to understand little bit about how do we use nanoclusters in order to degrade the perfluoroalkyl substances. Essentially, these are water pollutants. I will explain a little bit more about them. So, but before going into this particular topic, I wanted to give you some basic understanding about the quantum mechanics. So, a few topics of the quantum mechanics we will touch, and then I'll go ahead and introduce what are plasmons and what are the examples of hot carrier mediated reactions, and introduction to the PFAS, and how do we describe these plasmons quantum mechanically, and finally the final part that we did as the research. Okay, so if you already know the basics of quantum, just lift your hand, so we'll quickly go so that we can cover the other parts. Okay, so the first simple question based on the last talk, you should be able to answer these ones. Why do we compute energy? Answers. Stability of the system. Stability of this, to know the stability of the system. Answers. To know the dynamics of the system, you need to be a little bit more elaborate. Why do you need to know the energy? Why do we need to compute the energy for that? We can get forces, very good. So in order to calculate the forces, you need to know the derivative of the potential energy. That means you need to know the energy. So thermodynamics, entire thermodynamics is filled with so many energies, right? Gibbs free energy, internal energy, etc. Or if you wanted to deal with any biological system, you wanted to consider drug and protein interaction, you need to calculate the binding energy. All particular engineering sciences and normal sciences all needs energy, therefore you need to compute the energy. Now the question comes, how do you compute the energy quantum mechanically? You should solve the, so how do you, okay, before going that, how we can say simply, how do you calculate the energy classically? Classically he has defined, I was listening there. What is the energy is composed of? Kinetic energy and simply potential energy. For simple systems like you throw a ball or something, you know the velocity and then you calculate half mv square, that is the kinetic energy. And if it is in the gravitational field, you will calculate accordingly the potential energy based on the gravitational. But if it is an electrostatic force, accordingly you will be calculating also the potential energy based on the electrostatic forces. So in quantum mechanics, simply you will do the same thing. You will use what is called as the Hamiltonian. So first you need to write the energy operator. How do you write the energy operator? As we just now described for the classical case, it is summation of the kinetic energy and the potential energy. So all you need to know is, in quantum mechanics you deal with operators. So how do you describe the operator for the kinetic energy? How do you describe the operator for the potential energy? These are the two things that we need to know. So for the case of kinetic energy, what is kinetic energy? P square by 2m. How do you write P in quantum mechanics? H bar by I, dou by dou x. Yeah, caps you will keep because to represent the operator, but what is the formula is what I was asking. So if you consider P is nothing but, or P square by 2m should be some, sorry. So P square by 2m, if you wanted to write, this is nothing but minus h cut square by 2m. So if it is only one dimensional along the x direction, then this would look something like this, dou square by dou x square. So this is enough for you to understand how do you write the kinetic energy. If it is 3-dimensional, therefore dou square by dou x square plus dou square by dou a square, dou square by dou z square, all these three terms will be there. So if you write, that is the first part. So here I wanted to jump directly to the full Hamiltonian of an entire system. So as he has already answered earlier, if I wanted to calculate the energy quantum mechanically, what I need to do? I need to solve the time independent Schrodinger equation, for example. So in order to, when I am saying solving the time independent Schrodinger equation, what is there in that? It has a Hamiltonian and it has a wave function and energy. H psi equal to E psi. These are the three. H, psi and E are there. E is that one which we want. What we don't know is about H and the psi. So what I wanted to first tell you about is H. Okay. So Hamiltonian, as we discussed, it comprises of two quantities. H is nothing but kinetic energy and the potential energy. Kinetic energy part is very simple for us to understand. Okay, potential energy depends on the system, it will change, but kinetic energy is more or less very simple to understand. So as we have written, this is the kinetic energy operator. The moment we consider any system, as I have shown in the first slide probably, we can imagine them as bunch of nuclei and bunch of electrons. So how do you write the kinetic energy of the electrons? Kinetic energy of electrons is simply like this. Okay, so m, what is the mass? Mass of the electron, me, you will be writing in some coordinates, atomic units. If you heard of these units called atomic units, you will consider me is equal to 1. So therefore the first term corresponds to the kinetic energy of the electrons. What is the second term? Second term should be corresponding to the kinetic energy of the nuclei. There you are adding the masses of the nucleus. Third term corresponds to the electron and the nuclear attraction energy, right? So that is, you know that it is a Coulomb energy, right? They are interacting themselves among themselves with Coulombic forces. That should be 1 by r minus r. So here the Z corresponds to the charge on the nucleus. What is the next term? It is the inter-electronic repulsion. So when you consider the potential energy, we have actually three kind of interactions. One is electron and electron can repel with each other, nuclear and nuclear can repel with each other, nuclear and electron can be attracting with each other. So this is that attraction, these two are those repulsion forces. So this is simply the Hamiltonian overall. Okay, so for any system you consider, you can immediately construct the Hamiltonian. Constructing is not a big deal, but solving is the major issue for us. Okay, so the moment you constructed this particular Hamiltonian, you will realize that solving it will be very difficult. Therefore one of the commonly found approximations is what is called as the Born-Oppenheimer approximation. You might have heard it in various ways. The essence of that is, when you are considering electron and nuclear motion, they can be separated. This is the major important point. The electronic degrees of freedom and the nuclear degrees of freedom, both of them can be separated. This is the point about the Born-Oppenheimer approximation. So you might have heard this as clamped nuclei approximation, etc., etc. The essential part there is, you will consider that the nuclei as fixed and electrons are the ones that you are moving. Okay, if nuclei are fixed, what will be the kinetic energy of the nucleus? 0. So you can remove the term that corresponds to the nuclear kinetic energy, and if the charges are placed at a uniform places, you can immediately calculate them based on the Coulombic energy. So that is like a constant term. Okay, so essentially you are left with this term and this term. That's what you write it as an electronic Hamiltonian within the Born-Oppenheimer approximation. As I said earlier, there will be situations where the Born-Oppenheimer approximation will fail whenever there is an electron and the nuclear interaction will be very strong. In those cases, you need to consider this non-adiabatic effects. In general, this is what we will be interested in solving. Okay, so far we already understood how to construct the Hamiltonian. What is the next part that we need to know? Psi. Okay, so you all have done, how do you get the psi for a case of particle in a 1D box? The simplest example that you might have studied. You might remember the wave function form, but I am asking, how did you get that psi? Applying boundary condition. Any other answers? So solution for the differential equation. The moment you write the Hamiltonian means what? You have seen like this, right? This contains the differential operators, and what you wanted to solve is h psi equal to E psi. That is the one that you wanted to solve, which is nothing but a differential equation. It is a second order differential equation. So therefore you need to have at least two boundary conditions in order to solve it exactly, right? So this d square psi by dx square in a minus h cut square by 2m d square psi by dx square etc. equal to E psi is what you have solved. That one will give you the wave function. For what? For the systems that you have actually solved. So these are certain systems for which you have definitely solved. One is particle in a 1D box, or harmonic oscillator, or hydrogen atom, etc. All of these are single particle systems, right? When you consider particle in a 1D box, there is only one particle, whatever that particle you consider it as, electron, proton, whatever it is. Similarly, when you consider the harmonic oscillator also, you have only one particle. Hydrogen atom, there are actually two particles, but if you have actually solved the hydrogen atom, you know that the two particle problem will be reduced into two one particle problems, right? Like one is separate motion of the both electron and the proton as the center of mass motion, and the remaining part is what you are solving separately as the R and L part. Okay, so essentially that is also a one electron system, right? So these are the cases which can be solved analytically. All of you understand what is meant by analytically? Analytically means you can solve it using pen and paper. Okay, you can get a final relation, okay, that you can remember. Like if I ask you what is the particle in a 1D box wave function, majority of you will be telling, I believe. Can you tell? Sin n pi x by L square root of 2 pi L. Okay, good. So like that you can remember because there is some formula for that. Whereas the moment you go beyond the hydrogen atom, there is no way for you to have any analytical forms. From there you need to solve using the numerical way. Okay, that is what you will be generally doing whenever you are using this Gaussian or any other software package. Someone was asking from Gaussian molecular orbital pictures. So if you are using that, that's what you are using in order to solve. Numerically you have to solve these ones. So in these cases, so for that multi-particle problems, the eigenvalue problem can only be solved approximately, and the approximations include the Born-Open approximation for the Hamiltonian, and for the wave function you need to start with some of these simple principles called variational principle or the perturbation theory, etc. Those who did MSc here, they already learned what is perturbation theory and variational principle, but the major point that you need to know is, I wanted to just mention one point about the variational principle. So you know already how to write the Hamiltonian. The moment you write the Hamiltonian, you can solve it and you can obtain the wave function, but only for the simple systems. The moment that it becomes complex, you cannot guess the wave function. You do not know how to get the wave function. Therefore, you have to start guessing the wave function. Okay. So what does the variational principle helps us is, you guess any wave function, whatever you want. The variation principle is telling you that the guessed wave function, if you put there and if you get the corresponding energy, the energy will always be an upper bound to the ground state energy. Okay. So this is a big boon. Okay, you will realize it very soon. So you have Hamiltonian, you created wave function, you don't know how to solve. So I asked everyone, please give me wave function, please give me wave function. There are 1000 wave functions given by every one of you. I can put each one of them and get the corresponding energy, and I will choose that particular wave function that has the lowest energy, and I will say that this might be the most probable wave function. This is the point we are saying, number one. Number two, variational principle is helping us in a big way that it will always be an upper bound unless the person who gave me the wave function gave the ground state wave function. In all the other cases, the energy will always be above the ground state energy. This is again an important thing because I don't need to search for the energies both above and below. All I need to search is above the ground state wave function. One side is already taken care of. Is this point clear? So that's how the variational principle is helping. Perturbation theory also helps you in a different manner. We will not go everything in detail. So now we know that if you can somehow guess the wave function, we did not tell how you can guess the wave function, but if you know somehow to guess the wave function, then variational principle helps us in telling whether this will be a ground state wave function, whether it is close to ground state wave function or not. Okay. So in order to create the guess wave functions, how do you actually create the guess wave functions? For that you need to know something. So the simplest thing that you already know is only the 1 electron orbitals, because you have already solved only the 1 electron systems. The solutions of any 1 electron system are called as the orbitals. Okay, not everything is an orbital, only the 1 electron system solutions are what are called as the orbitals. So although we consider generally, we speak always atomic orbitals, molecular orbitals, etc. What you should immediately remember is, you are not solving for the entire molecule or for the entire atom. This is not what you are doing. You are doing some approximation that is allowing you to solve only 1 electron systems. Okay. So what is the 1 electron atom that you have solved earlier? Hydrogen atom. That is the only atom you have solved. There whatever you are saying is perfectly correct. That atomic orbitals 1s, 2s, 2p, etc. that you obtained are only correct for the hydrogen atom. The moment you go to the helium atom and when you are drawing this, these are all approximations. There are 2 electrons. So when you solve for the entire system, you are not going to get what we call as orbitals. This is not true. This is only an approximation where you are solving 2 1 electron systems and then you are adding some masala there in order to get the final wave function. Okay. So these are the orbitals. So there are 2 kinds of orbitals. One is spatial orbital and the spin orbital. The spatial orbital and spin orbital, like very similar to the case of mass or charge of an electron, spin is also a fundamental property of an electron. Okay. So when I say electron mass is there, how you are accepting, very similar way spin is also something fundamental property for the electron. Okay. But Schrodinger equation, if you remember, does not consider the spin by itself. Therefore, in order to account for this, we will be adding, like if I wanted to say where is the electron, in wave function what you will do, you will write psi of r, right? That r is telling you what, that where is the position of the electron, you wanted to describe the position of the electron there. Similarly, there should be a variable that needs to tell about the spin. That variable generally people represent using omega, okay? Sometimes it will be written as x. So this corresponds to, so the spatial component multiplied by the spin component is what is called as the spin orbital. So spatial orbital, as you know, as like just s orbital, p orbital, etc. Those are the spatial orbitals. These are generally solved by solving one electron systems. And spin orbitals are the ones that you need because systems contains electrons and electrons contain the spin. In general, when you consider the wave function of a many particle system, let us consider simply water molecule or a methane molecule, etc., that will have multiple coordinates. So this here x1, x2, etc. corresponds to the spatial or spin coordinates of the system. The moment you consider this one, what happens is you cannot simply write any product of any spin orbitals, okay? So as you can see here, if you consider the wave function, what you can measure, you might have studied about this Born's postulate earlier, what you can measure is only the mod psi square. All of you remember this? Mod psi square will tells you about the probability density. So this is what is like the wave function. If you consider the square multiplied by this will give you the probability. If you are considering the case of electrons, in general it is known through the experiments that electrons are indistinguishable, okay? That means you cannot distinguish between an electron and an electron. Because of this property, this probability must not be changing if the coordinates of any two electrons are switched. So if you consider here, this is the experimentally observable quantity. So if you are changing x1 to x2, obviously it should not be changing because the particles themselves are indistinguishable. This leads you to two different kinds of possibilities. If mod psi square, so let me write this. For simplicity, I am using only two coordinates. If I am considering like this, so let's consider these two possibilities, okay? What I am saying is, if you are changing the position of the electron from one place to the other, since you do not know the position of, since you do not know a way to identify this is electron 1 and this is electron 2, if you just do like this swapping, you should be never able to understand that. Therefore, this probability density and this probability density should be exactly the same. So what are the possibilities? What is the way you can equate both of them? Here, what are the two possibilities for you? Plus and minus, okay? So the plus case is what is true for the case of bosons. Minus case is what is true for the case of fermions. Since electrons are fermions, okay, these additional thing will come from the spin statistics theorem, but I am not in a position to explain you that. But this is the one that tells us that this minus sign corresponds to this. So this is what you will call as the anti-symmetry principle that you might have studied. So this is all coming because of the indistinguishability of the electrons. Because of the indistinguishability of the electrons, there will be an anti-symmetry in the wave function due to the exchange of the positions of any of the fermions, okay? So now, how do we find the wave function for a system of non-interacting electrons? So this particular part is somewhat useful for you if you are dealing with plasmons, because if you consider like a metal or a metal nanoparticle, what you will consider is conducting electrons are free to move and they are non-interacting with each other. So it is in this context this will be helpful for you. So for the case of a system of non-interacting electrons, what will happen is the Hamiltonian can be simply written as the sum of the Hamiltonians. This is like you have 10 electrons, none of them are interacting with each other. You do know that each one of them's energy is separately you can add to get the total energy. Therefore, Hamiltonians also can be simply added as one after the other, okay? So in this case, these are like the one electron wave functions that you are solving. So this is like H psi equal to E psi kind of a thing for each of the system. Now, if you consider what is the, if I have 10 electrons, what is the wave function of these 10 electrons? This is the question that we are asking. So all these questions are coming majorly because we don't know a way to guess the wave function. Okay, so the question that we are asking is, okay, I have a 10 electron system that are not interacting with each other, and you know the wave functions for each one of them. Okay, because you know how to solve the one electron equations. Now can you guess what will be the wave function? So the obvious answer would be like, okay, I will take the product of all of these one electron wave functions and I will give you, that should be the wave function. Okay, energies are additive, wave functions are product wise is what you will say. This psi HP, whatever we have shown as the simple product, is not correct. Can you guess why it should not be acceptable according to quantum mechanics, the rules that I have just told? Why the psi HP, the psi Hartree product? The previous one is called as the Hartree product. Okay, this is very famous. Like when you learn about Hartree-Fock theory, Hartree product is something that you will be generally encountering. So essentially, Hartree product is like you just take the each of the electron wave function and just take the product of that. So why this one is still not a good wave function? They are all independent. They are non-interacting electrons. That's what we have started with. For the non-interacting electrons only, we have written this one, but still this is not correct. The reason is you are still able to distinguish the electrons. You are saying, or you are assigning electron 1 to chi I orbital, electron 2 to chi j orbital, etc. Okay. The moment somehow you are assigning electron 1, electron 2, even though they are non-interacting electrons, you should never be able to identify an electron and put it in some place. This is not acceptable. So therefore, this is not correct. The way to avoid this is what is called as the Slater determinant approach. Okay, so here you can see this is the psi 1 2, this is psi 2 1. So this is how you were able to identify, distinguish them. You should not be able to distinguish means you put this superposition. Okay, this is what you will be learning about quantum superposition. You heard of it, right? So essentially, this is the point that you are bringing there. Okay, so the moment you put x1, x2, now you cannot assign x1 to either chi I orbital or chi j orbital. For both of them it is there. So this is what is the way in order to anti-symmetrize your wave function. You have created one wave function which is just simply the product, but that product I cannot take. What you need to do? You need to anti-symmetrize. Okay, so that's what is called as the Slater determinant. If you have 2 electrons, it is very easy for you to write like this. If you have n electrons, what you need to do is to construct this kind of a determinant. You know that if you change the determinant this side to this side, one column, there will be a negative sign, and if you make 2 of them to be the same, it will be 0, etc. So using these determinant rules, people have created what are called as the Slater determinants. These are the ones that are at least valid wave functions to start with. The moment you use this Slater determinant, okay, as an input, and if you try to solve for the time independent Schrodinger equation, if you use only the Slater determinant, then what you will come to is what is called as the Hartree-Fock theory. Okay, so again, these are the details. I will just quickly tell you so that you will be understanding what will happen. So you know this part, right? Like psi h psi, what does it give? That should give you the energy. So now this, whatever this phi is there, this is nothing but your Slater determinant. We have told that you have given some particular 1 electron orbitals, right? Like chi i's, those are nothing but the 1 electron orbitals. You used them to create the Slater determinant and used the Slater determinant and the Hamiltonian in order to create this part. So 1 electron values, if you remember, these are like the EIs. Oh, sorry. These ones, okay? These are the 1 electron eigen values, okay? For each, like you can consider 1s energy, 2s energy, something like that, okay? So what you will do is you will be optimizing this with the what is called as the Lagrange multipliers. If you heard of this, maybe in statistical mechanics or somewhere you must have come across this. So this is what you will be doing in order to solve this equation. Okay, essentially you are considering the Slater determinant and the Hamiltonian, and you are minimizing these orbitals themselves. Okay, if you minimize these orbitals, what you will get is the ground state wave function. Since these orbitals are also part of the definition of what you call as the Hartree potential as well as the Fock potential, both of them contains the density. Density is computed based on again these orbitals. Therefore, these equations must be solved only self-consistently. That means you will start with some guess 1 electron atoms, 1 electron orbitals. You put them in order to construct the wave function. Use the wave function in order to solve this particular equation. Again, you will do it in a repeated manner unless you consistently, self-consistently you obtain the psi. Okay, so all this boring story, whatever I said, will give you only the energy, one way in order to calculate the energy of a system. So essentially what you learned so far is what are the procedural steps in order to go to the H psi equal to E psi for a non one electron system. One electron systems was introduced to you in your quantum chemistry books. Okay. Now that we do know, so the next part would be to solve the time dependent Schrodinger equation. That will be little difficult. So in between we will have some little bit cooling with plasmons. Okay. So how do you what are plasmons? You might have heard about this earlier. So you know that metals do not have a band gap, therefore conduction electrons can freely go in response to the external electric field. As I said, these are, you can think as like a non-interacting electrons. Okay. These conduction electrons can be thought of as being analogous to the plasma or the free electrons. Thus, electrons in this plasma can only oscillate at certain quantized frequencies. Okay, these quantized oscillations are what are called as the plasmons. So, for imagination, you can see here. So, you have the electric field and you have a nanoparticle or a nanocluster. You know that electric field go from the positive direction to the negative direction. Therefore, positive direction starts here. Therefore, the electrons are coming this side. Negative direction is that side. The positive ions will be going that side. So, this electric field is going like this. In phase with that, there will be a plasmon that will be oscillating. So, this is what is the charged oscillations, collective oscillations of many electrons. You have a lot of conduction electrons within the metal or the metal nanoparticle. All of them will be oscillating. This is what is called as the plasmon. So, plasmons are, why they are interesting, they can be used in order to, they are promising alternatives to the traditional catalysis due to their ability to harness energy from the light. So, how do this whole thing will happen? So, if you assume that you have formed this plasmon in time in the order of like 1 to 100 femtoseconds, there will be a hot carrier generation. So, hot carriers means the energies. So, you know that generally for a metal or something, this will be the distribution of the electrons. This is like your valence band, this is like your conduction band. So, near the Fermi energy, there will be little bit amount of levels. But hot carriers means their energies will be much above the Fermi level. If it is an electron, it will be much above the Fermi level. If it is a hole, it will be much below the Fermi level. So, this we are speaking in the order of like several electron volts, like maybe 2 electron volts, 3 electron volts, etc. This much amount of energy will be there. So, these are called as excess energy carriers or hot carriers. Okay, these hot carriers can be used to drive otherwise very difficult chemical reactions because they have kinetic energies, extra kinetic energies. They can be used to break bonds that you cannot often break. Okay, so with time, so these carriers will be undergoing electron scatterings. They have high kinetic energies, they can come across other electrons and they can do this scattering, and they can also do the scattering with the phonons. That's how the heat will be generated, and this heat here can go up to several thousand kelvins. Okay, so that's the amount of heat that will be generated. In the energy picture or like band diagram, if you see, this is how it will be. The generated holes and electrons, hot electrons and hot holes will be there within the 1 to 100 femtosecond. Slowly they will start to thermalize because of the electron interactions. After some time it will come back to this normal way, but during this time there will be a lot of heat that will be dissipated to the surroundings. Because of this lot of heat, you can put any particular chemical there and you can break a bond if you want it, right? If you, like in general chemical engineering people, they can easily heat the systems, right, with the catalyst. That kind of heat you can get it here, or you can have a multitude of other processes. We will discuss that. So, plasmons exist in both bare nanoclusters as well as the passivated nanoclusters. And there were several applications for the plasmons, including the biosensors or sensing. This is because these nanoclusters can harvest light, okay, a large intense light you can harvest. So, this is generally what is used in the surface enhanced Raman scattering, etc., photovoltaics, medical imaging, etc. But what we are interested is to do the photocatalysis or hot electron chemistry. This is what is our interest, and specifically for the PFAS. So, these are the varieties of processes that you can think of. So, when you shine the plasmon corresponding frequency on this material, so essentially what are you shining? You are shining the light with a specific frequency corresponding to the plasmonic excitation. If you are shining that light, this can directly excite a molecule. So, now you can imagine that there is a nanocluster, near to that there is a molecule. Okay, what kind of events can happen is what we are questioning, and these are the possible events. One is you can directly excite the electron from the HOMO to LUMO. The moment you do that, what will happen? The system will go from the ground state. This is the kind of process that we all know through catalysis. But what we are saying now, you are exciting the system to an excited state where it can try to dissociate. Okay, excited state here you see it is like a direct potential energy is like this. So whatever that is there, that will slowly go to this place, but this place already the bond is dissociated for that particular system. This example, if you have done any chemical bonding course, you might have seen in the case of H2 plus molecules in their excited states, they will be dissociating exactly like this. They will go to the excited state and from there they will be dissociating. So this is one process. The other is like directly transferring the electrons from the metal or here the nanocluster to the lumos of the molecule. Therefore, there can be a excited anion or excited cation there that can just simply cross and break the bond. So what I am trying to tell you here is how a chemical reaction can be done within using this plasmons. This is the second variety. Third one is like you can get this hot electrons and hot holes within the nanocluster and they can be transferred directly if the levels of this nanocluster and the LUMO, if there is a overlap, good overlap, there can be a transfer of the electrons from there to there in order to create the transfer the electrons and thereby again the dissociation. Finally, simply the heat that we said earlier, because of this electron and electron phonon scattering, there will be a lot of heat. You can simply use this heat in order to go vibrationally excited states and from there you can also break the bonds. So these are varieties of reactions that can happen, and there are earlier examples of several examples of plasmon driven catalysis. So this first one corresponds to the dissociation of simple H2 molecule on a plasmonic AU nanoparticle. I'll just flashing just to show you what are the different kinds of reactions. These are like CO2 reduction. You can see CO2 converted to CO plus H2O, and you can also conduct coupling reactions. So this is like a CC coupling reaction here, like from the CO2 they made the ethane molecule. Similarly, NH coupling is also done earlier. Okay, so this is like NC coupling. And then there are varieties of like directly reducing the nitrogen to form the ammonia. You can see here decarboxylation, methane, CH bond activation. This is one of the favorite things for organic chemists. So CH activation you can do, and you can also do the CO2 reduction. So these are all like different varieties of reactions. So after seeing this literature, we asked the obvious question. So can we also dissociate a carbon-fluorine bond? This was our interest and this is what we have seen. Coming to a simple part further is about what are these PFAS molecules. So PFAS are the water pollutants. If you consider any hydrocarbon, you know that there will be carbon-hydrogen bonds. If you replace every hydrogen with a fluorine bond, that is called as a perfluoroalkyl substance. If you replace only some of them, that is called as a polyfluoroalkyl substance. So as you can see here, carbon-fluorine bond strength is about 130 kcal per mole. Compared to CC, it is just 83. So it's like about 50 kcal per mole higher. So carbon forms its strongest bond with fluorine only. So carbon-fluorine bonds are the strongest bonds. So if hot electrons, hot carriers can be used to do so many reactions, can we use to degrade or dissociate a CF bond was the question that we have asked. PFAS exist in varieties, like it's not that PFAS when we are saying these are water pollutants as I said, but these are not like one or two substances. There are about 14,000 varieties of PFAS are there, okay, based on the groups as well as the alkyl chains or the aromatics, etc., there are like many varieties are there. Because of the presence of this strong carbon-fluorine bond, perfluoroalkyl substances are used in wide variety of consumer goods, like when you are considering a non-stick cookware pan in your house, or whether you are going to a fast food packaging center, or when you are using a raincoat or paints on aeroplanes, etc. They all use carbon-fluorine containing chemistry only because it is very strong and it will not easily deteriorate. So that's the reason they have been using this in all of these things, photography, firefighting foams. If you go to any military bases, all these bases will be contaminated a lot with PFAS, majorly because they use these firefighting foams with PFAS, etc., okay. But at the same time, because of the carbon-fluorine bond is a man-made bond, it is not made earlier by biology. Therefore, the enzymes are not able to, naturally they are not evolved to degrade this carbon-fluorine bond. So the medium-sized perfluoroalkyl substances generally accumulate within the body, including kidney, etc., all parts they have shown here. Essentially they are accumulating. And how do they accumulate? They come to us, I mean we are consuming, not only human beings, all forms of life are affected by PFAS now. you get this either through water or air or through land, but majorly we consume this contaminated water. Because of this contaminated water we are consuming, we will be having the PFAS in our body. Okay, so these are all the paths through which you will finally get into the aquatic systems and how you take that. Once you take the PFAS, like these are the kinds of diseases like kidney disease, liver damage, low birth weight, etc., etc., you can see. Okay, so essentially what is the message there? If you consider, if you are consuming PFAS contaminated water, it is not good for you. You need to degrade somehow the PFAS. And it is not that I am making it up. You can see the studies based on the, this is based on the USA. You can see here, this is little old study 2016, but by that time itself there were many places where the PFAS are contaminating the system. So the generally accepted value is like about, at that time was like about 70 nanogram per liter or so, yeah, 70. So but you can see that there are many places where this 71 to 100 or 101 to 349 are there within the US. Same goes for here as well. Not only in the USA, also in India, specifically in Tamil Nadu, also in Chennai, there are many places where the PFAS contamination is there. This is again little older data, 2016 one, where you can see like various peaks are about 100, that means they are much higher. Very recent study from IIT Madras by Professor Indumati Manvannan, Civil Engineering Department, they did for the Chennai waters, Adiyar River and various other rivers they have done, and you can clearly see that all these values are clearly showing that there is like a high amount of PFAS is there. Okay, so obvious question is, plasmons, can we use the plasmons in order to degrade this PFAS which are dangerous for us, is the question. Of course the answer is yes, and we did that, but it's not that we have done it experimentally, we did computationally. So right now I have only 18 minutes. So I thought again little more deeply I thought of going, but considering that 18 minutes, I will quickly go. I will skip the derivation parts. I'll directly go to the results. Okay. So what we need to do. So again, it is easy to say that plasmons can degrade PFAS, but how do we establish that actually plasmons are the ones that are degrading the PFAS? This is what we were trying to understand. Okay. So that too we need to establish it quantum mechanically. Okay. So how do you do that? So plasmons, as we said earlier, are collective excitations. How do you prove that? First of all, this is a collective excitation, whether plasmon is there within the system or not. Okay. So for example, if you ask experimentalists, they will show a peak which is very high in intensity and they will call that this is the plasmonic peak. Okay. They might have their reasons to call that as a plasmonic peak, but for me to understand why they are calling this as a plasmonic peak is very important. Okay. Tomorrow someone else may come and say that no, that is not the plasmonic peak, then I will be in a trouble, right? So first I need to establish that particular any nanoparticle that I am considering, that must have a corresponding plasmonic peak. And if I am exciting the system at that particular plasmonic peak, then what it should do? It should be able to generate the hot electrons and hot holes while it is decaying. Okay. If hot electrons and hot holes are generated, then the next step for me is those hot electrons and hot holes should go and sit on the PFAS, the molecule that I am interested. Not just sitting, that should drive the reaction and break the bonds. So these are the steps that I have to prove to myself that yes, this particular cluster can have a plasmonic peak, and if I am exciting that system at that plasmonic peak, there will be a formation of hot holes and hot electrons. I have to demonstrate to you that hot electrons and hot holes indeed come. After that, the transfer of these hot electrons to hot holes to the PFAS molecule, and after transferring the dissociation of the bonds. All of these steps are required, and for this there will be a corresponding theory to first of all to do. So I thought of again presenting the theory, but I will be skipping the text. But I will just tell you the important points. In order to simulate this whole thing, what you need to do is, because this is a time dependent phenomena, you need to go through the time dependent Schrodinger equation. The variant of a time dependent Schrodinger equation is the time dependent Kohn-Sham equations. Okay, please remember that Kohn-Sham equations are again single particle, very similar to Hartree-Fock equations. Here also you will be dealing with one electron systems. That's why you are called them as Kohn-Sham orbitals. Okay. Now hereafter, whenever you hear orbital, you should at least remember that this is somewhere they solved only one electron system, not more than one electron system. They have solved only one electron system, but then they did some extra masala in order to make it full thing. That's all it is. Okay. So these are Kohn-Sham orbitals, and you know, very similar to time dependent Schrodinger equation, the time dependent Kohn-Sham equations also look like that. What we wanted to see is when you shine the light, there will be an induced density, and that induced density is oscillating, right, in the plasmon that I have shown. So one of the first things that we wanted to compute is the density as the response to your shining of the light. Okay, Density is the response after you shine the light. That's what we wanted to. So the density operator is defined like this. Again, like Hamiltonian operator, you have seen how you define. Similarly, you can understand this particular one if you know a little bit more, but we will leave that part. So once you have that, you have to solve this particular equation. This is the reason I have told you that story about the Hartree-Fock equation solving, but this is very similar to solving the Consham equations. Okay, so you solved these equations, you obtained the psi-n's. These psi-n's can be used in order to calculate the elements of the density matrix. Matrix means there will be elements, right? In order to calculate each of these density matrix elements, you will be doing this, and then you will use this perturbation, okay, delta kick perturbation. Some of you might have studied again delta function at least. So this delta kick perturbation is used because if you see a delta function, how does a delta function look like? It's like a spike. Here we are telling it's a spike in the time domain, right? So therefore, what is the corresponding thing, what is called canonical thing about time? Can you tell? For momentum, it is the position, like that. For the time, what is the corresponding space? Energy or frequency space. So whenever you have a delta function in the real space, then the corresponding momentum space, it should be spread over all the place, right? Like very similar to Heisenberg uncertainty principle. So we use a kick pulse here because we wanted to understand the absorption of the system for all the frequencies. You wanted to know where your system is absorbing the light, right? In order to know that, what I need to do, I need to send a pulse that is very, very narrow. If it is very narrow, then it can contain all the possible frequencies, okay? So that's what we are trying to do here. The moment you do this, you will be able to obtain the, here this is resolved in the frequency space. This is the induced density, you can see this, right? Rho of t minus rho of 0 is the change in the density or the induced density with time. That if you do the Fourier transformation, you will get it in terms of the frequency space. So if I am shining green color light, what kind of induced density will be there? If I am shining red color light, what kind of density will be there? Can be obtained through this particular equation. Does it make sense to you? We are doing only the Fourier transformation there. That's all, nothing beyond that. Okay. So then these are the implementation details. I will skip that. But at the end, what you need to know is about the dipole strength function. This is related to the absorption, that is related to the dynamical polarizability. So this is the induced density and this is the dipole moment. You might remember that dynamical polarizability is nothing but dipole moment per unit volume. That's what is the this one. So this density is like per unit volume. So therefore these two will be there. So finally you can write this induced density in the real space, and this is how the induced density would look like. Okay. So what you are seeing here clearly is the separation of the positive and the negative charges. Okay. So this is one way to prove that my system contains the plasmon. If plasmon is there, then there should be an oscillation of the densities, charge densities, and that's what we have seen here. There is other way to establish, which is through the time. I will show you once. So this is what is the transition contribution map. So this is additional one that through which we can show this. So what this does is, like, once you have this absorption spectra, I just calculated the absorption spectra. So this is your absorption spectra. You have many peaks here, right? Which peak corresponds to the plasmonic excitation? This is what we wanted to do. One thing is, like, you shine this on the system at 3.83 peak, and then you check this induced density. If the induced density is like this is one way to confirm that there is a plasmon formation. There is another way to confirm, which is you take this peak, you divided it into various excitations. So all of you are aware of this normal picture, right? Electron pictures, molecular orbital picture, right? Like this. So you can say that this is something like a Fermi level. If not Fermi level, at least this is the one. And then if it is like a molecule, this is like the HOMO, and this is like the LUMO, and all the other ones, right? You know that below this, all of them are filled. Above this, all of them are empty. When you are doing this excitation, what will happen? When you shine the light, all of you are again aware of this. This particle will go and sit here, and there will be a hole here. And what are the possible excitations that are feasible? It can go from HOMO -1 to LUMO, HOMO -1 to LUMO +1, and so on and so forth. So each excitation peak that we are considering, this is a peak if you are considering, that is an excitation peak. This corresponds to various transitions. Okay. Each one of this is called as a transition. This is called as an excitation. So each excitation will contain multiple transitions. Okay, so the moment you understand these transitions, what you can do is, if there are multiple transitions that are leading to this excitation, because this is a collective excitation, therefore you can consider that as a plasmonic system, plasmonic peak. But for the same peak, if I am considering for example this peak, and again I will do this distribution, how many transitions are leading to this particular excitation. If the number is very less, then I will call it as non-plasmonic peak. Is this clear? How am I distinguishing? One is through induced density, another one is through transition contribution map, how each transition is contributing. Here in general, in this map, you can see that this is given in, this is the occupied, this is the unoccupied. So from here to here the excitations are happening. You can see this black line that you are seeing is called as the resonance line. So that means if you are shining the light at 3.83 electron volts, if there is a excitation corresponding to that, that will be shown here. There are only very few mild excitations at that particular say, but there are, you can see multiple excitations that are far below the diagonal line. So these are the collective excitations that are leading to the formation of the plasmon. Okay, so this is another way through which we have proved that there is a plasmon within the system. So now that the plasmon is proved, I thought of explaining more about the TCM, but I am skipping that part for now. Now, second thing is to establish the generation of the hot carriers. How do you prove that? For that, what needs to happen? The plasmon has to decay, and what we call as now resonant excitations have to start. So when we saw this previous picture, in this picture you saw that this line corresponds to the resonant line. Since these excitations are away from the resonant line, this ones and these ones, these are called as non-resonant excitations or non-resonant transitions, to be precise. Okay, if any transition occurs here, that is called as a resonant transition. Resonant transitions corresponds to the hot electrons and hot holes. Okay, non-resonant ones corresponds to the plasmon. Okay, so now we can simply do, again I'm skipping the details. So this is the laser pulse with that particular frequency. We shine the laser pulse and we immediately see how the dipole moment is changing. This is what we will be checking. As you can see, in the beginning the dipole moment slowly rise to very high value. The reason is you are shining the laser, so accordingly there is an induced density that is oscillating from this side to this side because your electric field is oscillating. Okay, and slowly the dipole moment is falling. Although the pulse has gone, still the dipole moment persists even at 20 femtoseconds or even 25. Slowly after 25 it is slowly vanishing. So this means plasmon has generated, but the plasmon is decaying, is one part that you can directly see from the this particular dipole moment plot. Next we have plotted the total energy. If you see the total energy, we have divided it into the non-resonant, resonant and the Coulomb part. You can see that in the beginning everything is there in the non-resonant, this blue color line. Okay, that means it is corresponding to the plasmon. The plasmon is again slowly decaying and the resonant part is slowly increasing. That means more and more hot carriers are slowly generated within the system. Also you can see the Coulombic part is slowly dying off. Coulomb kind of interaction will be there when there is positive and negative is changing, right? So during the plasmon oscillation time, the positive and the negative one will be very far from each other. Therefore, you can see this rise and fall. Okay, as it goes to this end, because plasmons are completely gone, you will directly see the Coulombic interactions also dying off. So this proves the generation of the hot electrons. In addition, we can also see this in the beginning. You can see that there are non-resonant transitions, or whereas at the 27th femtosecond everything fall within the region, proving that the generated ones are hot electrons and hot holes. Same goes for this other part, how the hot electrons and hot holes distribution is there. Also we can see as the time is progressing, in the beginning majority of the hot electrons are only there closer to the Fermi level, but as the time is progressing you can see that hot electrons with about 3 electron volt energy etc. also can be generated. So once you have done that, the final point that we need to prove is the transfer of these hot carriers to the p phase. So we did that as well. Again, there are multiple possible processes are there. I have explained you about this indirect process where the electrons and holes are generated within the nanoparticle and then they are transferred to the molecule. Other one is the direct transfer where electron will be jumping from here to the molecule itself. This is useful because that will not lose any energy within the nanoparticle. If there is a generation of the hot electron or hot hole, then there can be electron-electron scattering. Nanoparticle will have lot of electrons, therefore there can be electron-electron scattering and it can lose the energy. On the other hand, if this electron can directly go and sit onto the molecule, it will not lose its energy, therefore driving the chemical reactions will be very nice. So how do we improve this efficiency is some part that we are currently dealing with, but this is something, if you can improve the direct charge transfer efficiency, then you can make the bonds selectively. Also you can break a specific bond. If you have like CBr-ICl like that, you can specifically break Ci bond versus CBr bond. This is feasible, provided you know what is the potential energy surface of that. Other one is the simple excitation. So what we are going to see is this DHET values. So you can see that majority of the transitions or majority of the transfer is happening within the nanoparticle to nanoparticle. The general from the particle to the molecule efficiency is very low, but still that is happening, that is this green color, and this is the distribution of the hot electrons and hot holes. Here you can see with more than 1 eV energy how the hot electrons and hot holes are there. Hot electrons went to the PFAS molecule, whereas the hot holes majorly staying on the nanoparticle. So between hot electrons and hot holes, which can decompose the PFAS? Possibility at least only the hot electrons, because hot holes are entirely staying on the nanoparticle itself, or nanocluster in this case. So then finally we need to simulate that one. We have simulated, and you can clearly see here that the carbon fluorine bonds, here the equilibrium bond distance is about 1.37 or so. So when we do this Ehrenfest dynamic simulation, so these are the non-adiabatic dynamic simulations. Both ions will move and the electrons you will be optimizing at every step. As you see with the time, several of the carbon fluorine bonds are dissociated, and if you plot these bond distances, you can see that they went up to 3 or more than 3 angstroms, proving that these can be decomposed. So that's the rough conclusions. Like we have proven quantum mechanically the existence of the plasmon, and there I have shown partially the spatial as well as the energetic distribution, hot carrier generation, and finally the PFAS degradation. I wanted to take one more minute. So in general, for practical utilization, hot carriers need to be transferred to the environment before electron-electron transfer scattering takes place. As I said, if they are sitting within the nanoparticle, it is not good. You have to try to push it towards the molecule. Can occur indirectly or directly, as I have mentioned. So both experiments and calculations indicated that hot carriers generated in the metal can quickly relax through this scattering, so which renders the indirect pathway is inefficient. So we need to create more efficient direct transfer processes. This is one area that we are working. So what are the things that we found so far is like changing the shape and size can be simple things that you can do. In addition, transition metal doping can help you in order to directly increase the hot carriers, okay, specifically hot electrons. We are still working on that. So this will be one important thing to look for. If we can achieve, then we can drive chemical reactions in the way that we want. Okay, that this works are majorly done by Pramod, Samir and Kushbu, and these are the computational resources we have used, both IIT Madras as well as Param Porul, NIT Tiruchi, and IIT Kharagpur Param Shakti, and all the centers. And I would like to also thank Professor Pradeep for giving me this opportunity for presenting here. Thank you all for your attention.
Very nice talk. I wanted to know that what is the difference between plasmon sitting in a nanocluster and a nanoparticle and bulk also?
Nanoparticle, nanocluster and
Bulk.
So again, the major difference would be like how it will be decaying, not in how it will be created. The creation will also have a difference, but it is majorly about how many number of electrons are coming together in order to form this. So if it is on a surface or something, that can go continuously, that can propagate, whereas in a nanoparticle or a nanocrystal, it will nanocluster, so it will not be able to propagate further because it is confined there by the boundaries of the system. So the decay channels will be completely different there. If you consider a metal, the large number of bands will be there, so electron scattering will be huge there. So majority of the times it is very difficult for you to harness these hot electrons or hot holes there. So therefore people try to put semiconductors etc. on top of these ones, so that at least some portions will be taken from there. So that will be the major difference, I would say.
In this plasmon-induced PFS, what is the product?
So right now, like it's only the Ehrenfest dynamic simulation we did in the gas phase. So here, like you are seeing all the bonds are dissociated. For our purpose is whether we can degrade or not. So, but if you do, like I have done earlier, like ab initio molecular dynamic simulation separately with water on various metal surfaces. Depending on the metal surface that you consider and the water molecule, you can get variety of products. For example, when I did with calcium surfaces, I found CaF2 kind of substances were forming. Or in general, you will see this HF, but HF is not like a what you call stable product. It is like a transient one. It can again dissociate into H plus and F minus within the water. But if you consider systems like calcium, they can give rise to environmentally benign products like CaF2.
If I add calcium from bio, and if I do the reaction, then I can get CaF2 as a.
I believe so. But at least I have done the calculations. Those are showing anything and everything as long as the energy is sufficiently available. So as we have shown, like CO2 reduction, N2 reduction, these are the major things that all of catalyst persons are looking for. All of these can be done is what they have shown already. So anything is feasible because all the strong bonds are like N triple bond, N is one of the strongest bond which we wanted to reduce, that they have done. CO2 is something that everyone is worried about, that also they were able to do. And from CO they have considered and they even made the CC coupling, that also has been done. So
just before your talk, Uli Heiss was talking about support, how supports are important in the case of clusters for catalytic processes.
Okay.
And obviously, your clusters, what you talked about, in reality will be used on something.
Correct.
Right?
Right.
So how do you synergetically utilize this?
So again, as I mentioned to him, like you might need to consider some semiconductor containing surfaces that would be more useful so that you can harness these hot electrons and hot holes. That would be the ideal thing. Like TiO2 and others were like the ones that I have at least seen, came across earlier.
Well, in the experiment that was shown by Uli Heiss, the moment the platinum-18 cluster is put on TiO2,
oh, they also
TiO2
consider that.
is
Okay.
not the same.
Okay.
So many things happen on the TiO2. TiO2 get covered and things like that. Lots of interesting possibilities are there which make or may not make the catalyst system active. In this case of platinum, it makes it active. So there are additional issues to be considered, and so therefore, a lot more opportunities are there. Is the
definitely
message?
Yes, definitely. Okay.
Thank you, sir, for showing that how quantum models and light together can challenge the unbreakable.
Thank you very much.
All the very best to you
Thank
for
you.
the next activity.
Yes, thank you.